Well, welcome back, guys, and I do hope as ever you and your family are keeping well. So this is our 6th lesson on electric fields, and what we're going to look at today is an experiment to measure the permittivity of free space and perhaps the relative permittivity as well. And then we're going to look at a very, very famous experiment that was done to show that the charge on electrons is quantized, an experiment called Millikans Experiment. So let's kick off with an experiment that we could do in the laboratory, though I'm going to do it theoretically on the board, to actually get a value for the permittivity of free space and then possibly the relative permittivity of different dielectrics. Now, if you remember, this is about how well electric field forms in space. And what we're going to do is we're going to use a parallel plate capacitor, and we're going to change the potential difference across the capacitor, in other words, change the voltage across it. And for every value of voltage, we're going to measure how much charge is stored on it. And then we're going to use those readings to draw a graph. And once we've got our graph, we're going to use that to work out the permittivity of free space. So let's get started. So what we're going to do is we're going to set up an experiment to find or determine epsilon naught, and I can show you how we can use it to find epsilon r as well practically. And if you remember, if we multiply those two together, so epsilon naught, epsilon r, where epsilon naught has some units, some dimensions, and epsilon r is just a multiplier, a dimensionless constant that tells us about the dielectric. If you remember, those two multiplied together gives the permittivity of the dielectric in a capacitor. So, take me a little while to draw this, but I'd like to draw it in front of you. We're going to charge a capacitor up with a power supply, and typically this is an EHT power supply, extra high tension. So it's thousands of volts, kilovolt power supply. It's actually the one that I use at the beginning of these videos to get that little clicking sound of the sparks, the arcing, and the purple spark that you see. So a power supply unit and extra high tension. So high voltage. It doesn't have to be, but it works best if we use one of those. Okay. And then what we're going to do is we're going to take some parallel plates. And these are usually the size of sort of trays that you'd eat your lunch off. Okay, maybe half the size of a tray. So I'm not going to draw them in like a three-dimensional diagram, but clearly they're sort of this sort of size. Okay, and you can measure the distance between them, and you can measure the plate area, their surface area, quite easily. So we're going to connect that to our power supply, and what I'll do is I'll take the negative of the power supply, or we could consider that to be grounded, okay, the minus, or we could just bring it down to earth so we know the potential on that is 0, and we'll connect that directly to the bottom plate. It's just an easy way of drawing this, okay, and then we'll carry that on. And we're going to measure voltage, okay, so I'll put a capital V here. That's typically a meter on the front of the power supply. And we're going to measure the charge stored on the capacitor. Now, the way we do that is with a Coulomb meter. I can't remember if you've seen one of these things, but a Coulomb meter, just a device you can get from the store, from the technician. Okay, and it reads, ours read in microcoulombs, so I'll just put a number on here, 0.12, nanocoulombs, not microcoulombs, nanocoulombs, 10 to the minus 9 of a coulomb. And it has two connections. It has a connection on top that we can connect one side of the capacitor to, okay, and that's typically the grounded side. And then what it also has is a little sort of connection here which we can connect the positive to. But normally we connect into that a little metal sort of T shape. Okay, it's a little disc on a metal bar, so it just means that we can like touch a wire onto it easily. We could, of course, just plug the wire in. Now, you might remember from practicals that we've done the idea of a flying lead. So here's the positive of the power supply. Out it comes, and we'll have it coming to this point here. Okay, and then what we're going to do is we're going to connect this plate of the capacitor. So I'll draw it in red, the top plate, to a flying lead. In other words, a lead that we can connect into here if we wish to, and that will charge the capacitor. Or we can flick the lead over to the right and discharge the capacitor into the Coulomb meter. So I will just write on here for the sake of completeness that this fella here is a Coulomb meter. So it's going to measure the amount of charge on the capacitor in nanocoulombs. So we select a voltage on our power supply, 1000 volts, connect the capacitor to it, and then disconnect. So that capacitor has now got 1000 volts across it, and then touch it onto a 0 Coulomb meter, and we can write down how much charge has been stored for that voltage. Now, you might say, but hang on, can't you do this because you know how much charge is stored because you know the capacitance? No, you don't. Okay, it's a little bit subtle, this, but if these are just two metal parallel plates that we've just got out of the cupboard, and we've just, put them on a stand, isolated them and had a gap here, we don't actually know its capacitance. So we can work it out, obviously, if we know the voltage and the charge stored. And then we'll increase the voltage by an increment, charge up the capacitor again, discharge it, etc. Just for interest's sake, the resistance in this circuit and this one we can consider to be very low. So the time constant, CR, is going to be very short. So we don't have to connect and count and wait. It's basically instant charge, instant discharge. Okay? So we're going to collect those numbers, voltage against charge stored on a table, and I'll show you now what we're going to do with them graphically. Okay, so what I've shown here is a little table of data that we might collect, and I've done that on purpose to say we'll compare the charge to the voltage, but remember the charge is probably in nanocoulombs and the voltage might be in kilovolts, so this might go 1, 2, 3, 4. Just be very careful in exams you spot that it's not in coulombs and it's not in volts. Okay, so let's look at this a little bit more mathematically. So what do we know about capacitors? Well, you might remember that the formula for capacitance is epsilon, and that's typically epsilon naught, though it could be epsilon naught multiplied by epsilon r, A, the surface area of one of the plates, divided by the separation between them. Okay, and also we know Q is equal to CV, so therefore we know the capacitance is Q over V. Okay, so what we're going to do is plot a graph of Q against V. So I'll just draw my axis here. So to make life easy, on the y-axis we'll have the charge. I think you can see why. And on the x-axis we'll have the potential difference, okay, the voltage. Now, this is just a sketch graph, if you see what I mean. It's sort of, I'm not plotting numbers, so I'm not going to say Q in microcoulombs, volts in kilovolts, etc. We're just going to plot Q against V as an example, a sort of generic example. Okay, and obviously, because the capacitance is constant, because we don't change the separation between the plates, and we don't change the surface area, okay, then Q over V, the capacitance, will be constant. So we'll end up getting a straight line. And those of you who know me well know that I'm pretty obsessive about the fact that straight lines are not always at 45 degrees. Okay, I'll just draw one on there. Now, if you look at this, Q over V is constant. Of course it is. It's the capacitance. Okay. In other words, it's the gradient. It's the gradient of the line. Okay. Which is the capacitance. But do you remember that C, the capacitance, is also equal to epsilon, which we have no idea of at the moment. Shall we argue this is an air-spaced capacitor, so the relative permittivity of air is about 1.0003 or something like that. Okay, so basically it's a vacuum. Yep. So this is really epsilon naught. We can measure the surface area of one of the plates, and when I used to do this, I've done it with square plates. I've also done it with circular disc. You've seen those in some of my videos, I think. Circular disc-shaped plates. It doesn't matter as long as you get the surface area of one of them, okay, because that's the one that the charge has kind of been pulled off and put onto, if that makes sense. Okay, and we can measure their separation with a ruler, or you could use a vernier caliper where you use it with the pointers pointing outwards, if that makes sense. So you clamp all of this. You make sure it's the distance between each plate is even, so they're parallel. It doesn't matter what angle you do it, as long as they're very parallel. You measure that distance, typically about half a centimetre. Okay, so be warned, it must be in meters. Okay, remember you'll measure the plates probably in centimeters. No, do it in meters. So this must be in meters squared, and this must be in meters. Okay, so we know the capacitance is epsilon A upon D, and we know the gradient of the graph is going to be the capacitance, epsilon naught A upon D. Okay, so all we need to do here is that if C, the gradient, so you calculate the gradient by drawing the biggest triangle you can, is epsilon A upon D, then we can rearrange this for epsilon. Yeah, A comes underneath, so C over A, and then the D is a multiplier. So there we go. That's a way that we can work out epsilon from our experiment and from our graph. Now, the thing I wanted to point out is, really, because this is a vacuum, it's air, that will be epsilon naught. Okay? So think about how you'd find epsilon r. What you do to find epsilon r, of course, is you'd put a dielectric in here. So you put your sheet of thick plastic or thick rubber in the gap, or maybe a stack of paper, okay? And then that would give you the gradient, working it out this way, would give you epsilon naught, epsilon r multiplied together, and then you just divide by epsilon naught, and you've got epsilon r. And it'll be a number, hopefully, like 3, 4, or 5. Okay? So, a nice little experiment there that will enable you to work out the relative permittivity of free space, and also, the permittivity of free space and the relative permittivity of a dielectric that you put between the plates. Okay, so now let's look at Millikans Experiment. This is right on the verges of your specification. I don't think you need to know this in detail, but there's no reason they can't set a question about, here's an experiment, explain what's going on. Okay, and this is named after Robert Millikan, who did some amazing work trying to find out what the charge was on the electron. Now, there's a bit of background to this, but very quickly, think about the sort of time. J.J. Thomson, plum pudding model, had sort of discovered the electron as being a negative object that came out of a positive amount of atomness. Okay, and Millikan took that work a bit further and tried to see what the charge was on these electrons. And it's quite interesting because he did that work at the University of Chicago. I've got to be careful what I say here. At a time when nearly all the great nuclear physics stuff was being done or had been done in the UK, Cavendish Laboratory particularly, in Cambridge. So let's have a look at what Millikan did. And oh, by the way, he got a Nobel Prize for this and some other work in 1923. Now, I'm going to massively simplify his experiment. But what he showed was, and it's incredibly clever, he showed that the charge on electrons was quantized and it had a single value. In other words, he determined the elementary charge. Now, I'll sort of point out that that's kind of a minus E because he wasn't working with free protons here. He was working with electrons. And just remember that E, the elementary charge, 1.6 times 10 to the minus 19 is the charge on a proton. It's not minus 1.6 times 10 to the minus 19. That, of course, is the charge on an electron. But we'll get there in a minute. Okay, so let me show you what he did, and it's really very, very clever indeed. And you'll see the connection with parallel plates and capacitors. So I'm going to hugely simplify this. So if you look this up, you'll go, well, hang on, your diagram isn't exactly what he did. And you'll see differences, but it's the concept that I want you to get. Okay. So what he basically did was set up a pair of parallel plates. The next thing he did was connect those to a power supply and make the top one positive and the bottom one could be grounded or negative. It doesn't matter for what I'm going to do today. Okay. Then, and here's the clever bit, okay, he took basically an aerosol can. Back in the day they weren't. It was a squeeze, squeeze, squeeze perfume type sprayer. An oil can that we use the term atomize, but of course we're not turning into atoms. Something that will produce a very fine spray of an oil, okay? So you get very, very fine dots of oil. So I'm going to draw the little sprayer here. So here's the nozzle, and I'm going to make the nozzle quite narrow, so you could consider it's a sort of aerosol type thing. And then we're going to go up here to a squeezy bulb that he could squeeze. It's interesting physics how these things actually work, Bernoulli's principle and all of that, but that's for another day. Okay, and in here is some oil. Right, okay, now you don't need to worry about how this works, but basically squeeze, squeeze, and out of it comes a spray of tiny droplets spraying into the gap here. Now, you need to see these droplets, so I'm going to draw the observer on this side. Okay, you might be familiar that physicists use this funny eye shape to say, look that way, guys. Now, these droplets are absolutely minute, so I'm avoiding a lot of detail here. There's a microscope here and everything else. It's a really fiddly piece of apparatus, okay? I'm reminded of alpha scattering, not a dissimilar size, and, really tedious. You're having to get in there and look very, very closely. It's pitch dark inside the apparatus, so he had to illuminate it. And something interesting about the droplets. So I'll draw some drops in here, and they're massively magnified. Okay. they're hugely magnified. Now, I'm making a very important point here that these drops are different radiuses, okay? But, and that's a key point here, okay? There's a whole range of different sizes of oil drop. Now, what he did was he charged up these drops, and let's say that we made the drops negative. Now, what I'm going to do is I'm going to connect the metal nozzle of the sprayer to the negative plate. Okay, this is where physicists who really know this experiment well are going to go, what, FJ? That's not what he did. I know it's not what he did, but it keeps life simple. So this is a metal nozzle, out come the oil, they've been connected to a negative place, so they are going to be covered in electrons. They're going to be mini sort of free capacitors. Okay, what he actually did, is you can use X-rays, and you can fire X-rays in, and the X-rays will ionize the drops. But I'm simplifying to show the concept that's so important. Now, these drops picked up different numbers of electrons. Okay, so maybe that one picked up 1 electron, obviously a lot more than that probably. This one might pick up 2 electrons. This might pick up a few, maybe 4. And this might pick up, I don't know, 3 electrons. Okay, now you're going to get lots and lots of drops in here. And now we need to look at the forces acting on those drops. Okay, so remember we've got 2 fields in this gap. Okay, or 2 important fields. There's no moving charge really, so there's no magnetic field. Okay, and we forget the Earth's magnetic field. But there's a strong electric field, and remember the field lines go from plus to minus, okay? So a uniform field acting downwards, okay? But the electric field is the direction a positive charge would move. So you can see what these guys are going to do. They're going to feel a force upwards due to the electric field. But here's the clever bit. They've got some mass, and therefore they have a weight, so they're going to feel a force downwards due to the gravitational field. So let's have a look at those 2 fields then. So we've got the weight of the drops, W, will be equal to mg, so that will be the force downwards on each one. And now we need the force upwards on each one. Well, you might remember that the electric field strength is defined as the force per charge. Oh, I see, we just rearranged that, yeah? That the force on those objects, upwards, will be EQ. Okay, now whether that should be a little q or a big Q, let's not worry. Now, here's the important point. Do we know E? Yeah, okay, well we know E because E, the electric field strength in parallel plates, is V over D. Okay, so we don't have any problem working out E. Now, do we know F on these going upwards? No, we don't. We'll come back to that one. Okay, but do we know F downwards? Well, we do, but this is quite complicated, so bear with me. We know G is 9.81 meters per second squared. But what are the masses of all these different drops? Well, that's partly where the microscope here comes in, okay? Because if you can look at those drops and get their radius, okay, with a little graticule scale within the microscope, then you can work out their volume. And if you know their volume and you know the density of the oil, isn't this clever? You can work out, knowing the volume and the density, the mass. Because density, shall I put that here? Density, maybe rho, is mass divided by volume. Okay, so we've got a set of equations here, and you might be a little bit worried about F upwards. We'll come back to that. No idea what that is. We can't put a Coulomb meter in here and do some measurements. I have no idea what Q is. Okay, so let's have a look at what happens to these drops. Well, this one is quite light, okay, so it has a small mg downwards, but it feels a force upwards due to the plate here, and that force might be very small. Okay, so that's the force upwards. Now it's a bit difficult to see here, but if the weight is bigger than the force upwards, can you see that that drop will fall down? Okay, removed from the system. Yep. This one here, okay, it has much more weight. So mg. I need to draw that line, sort of bigger than this one. But it's got 4 electrons on it, and shall I argue that this one feels a force upwards that's the same as the weight? Okay. This one has got, what has it got? 3 electrons on it. So this is going to have mg downwards, maybe the same as that one. But the force upwards is not going to be quite as big because it's only got 3 amounts of charge on it. So this one's going to fall downwards. And shall we argue that this one with its 2 electrons, just for interest's sake, has a very small weight, probably the same as that one, mg, and a big force upwards. So due to the electric field. So that one's going to go scooting up and hit the plate. Okay, I won't draw that one now. I think you get the idea. The point I'm making is, look at this one, and there will be many others that are like this one, where the weight is equal to and opposite to the force due to the electric field. And I'd like you to consider, therefore, that this one will hover. It'll just sit there. Okay. Now, what about one that was much bigger? Well, if it's much bigger and it's got many more electrons on it, it will feel a bigger weight and a bigger force upwards, and it might hover. Could I draw a smaller one here? Yes, I could. Okay, with maybe 3 electrons on it. So the weight downwards is less, but the force upwards is a bit more because it's got 3 electrons, and that one could balance out as well. So in summary, what Millikan did was he looked at all of the oil drops of all different sizes, okay, and picked all of the ones that hovered. So big ones with a lot of charge, small ones with very little charge, okay. And then he kind of divided the small ones into the big ones, okay. A little bit of maths went on, and what he found was that never mind what he did with his maths, there was a smallest number that kept coming up, okay? That there didn't ever seem to be a number that you could divide in again. In other words, and I'm waffling here now, and all the textbooks waffle on this, that there was an oil drop that might have 1 electron, or a bigger oil drop that might have 2, or 3, or 4, but never anything in between. It was a bit like a kind of integer value type thing. And so what he noticed was that there was an amount of charge the drop could have, or twice that charge, or 3 times that charge, or 4 times that charge. And indeed, he'd shown that the charge on the electrons, the elementary charge, was quantized. It comes in discrete chunks of 1e, 2e, 3e, 4e, etc. Incredibly clever. Okay, so what's important about this for you guys is, I guess, the equations you should understand and know, how parallel plates and fields form in parallel plates, and I hope you can appreciate there are some arrangements of oil drops where their weight, whatever that is, can be counterbalanced by the force due to the electric field because the amount of charge on it is correct for that weight. Now, a couple of other things to say before I finish on this. I've said already that his experimental setup was much more complicated, but this is enough for you guys, okay, and for me. It's also worth saying that he there's air in here, and the air makes things much more complex, and he used the viscosity of air to work out various things about how the oil drops drop as well. So, it's pretty complex physics, but I've tried to massively simplify it. But finally, and I don't know if I'm getting my story totally right, okay? But the story goes that Millikan picked data from his experiment that looked good and ignored data that didn't look good. And scientists have been back through his laboratory notebooks, and I'm told they've actually found bits of data which were good, were correct. But because it didn't quite fit with what he had in his head, supposedly he ignored it or crossed it out and published. And he published a value for the elementary charge on the electron that was not really quite correct. But he's a Nobel Prize winner. Okay, everything you learnt in GCSE, highly respected scientist. So every other scientist, like me, people who aren't so well known, though I wasn't around during that time, repeated his experiment and did experiments in different ways and didn't get Millikan's answer, so they must be wrong. So what are they doing wrong? Okay, but in fact, they might have been right. Okay, and the Nobel laureate may not have been as close to the real answer. And Richard Feynman, who's a wonderful physicist, did a nice little bit on this. But basically, it took time for scientists who weren't so famous to kind of stick their head above the parapet and go, don't think Millikan quite got it right. I think our answer is closer. And slowly but surely, we homed in upon the fact that the elementary charge comes out as 1.6 times 10 to the minus 19 coulombs. And you'll remember perhaps when you were younger or last year, you might have even written down answers to questions which had the charge on some object as being sort of 1.1. It just can't happen, yeah? But this is the elementary charge, and you can only ever have multiples of it. So a very, very clever experiment with a lot of interesting history behind it. And that is Millikans Experiment. Good. Well, I hope you found that both interesting and useful, and a little bit of history of science there with Millikan's work. I'll be making another video soon, and as ever, I look forward to seeing you then.